All right, today we're going to look at exponent rules, exponential equations, and logarithmic expressions. So we have talked about exponent rules before, so this is just really a review. The product of powers. If you have two terms being multiplied and they have the same base, such as here, recall that we add those exponents. So this would be equal to a to the m plus p power. So the bases must be the same. And again, you add the exponents. So why don't you go ahead and pause the video and practice 1, 2, and 3. And then when you're done, you can unpause and we'll check our work. So looking at question number 1, you can see the two bases are the same. So since the two bases are the same, we can add those exponents. So this is 5 to the 2 plus 4 power, which is 5 to the 6 power. And because this is numerical, we can plug that into our calculator to get 15,625. Anytime it's numerical, you always want to calculate what the value is equal to. Looking at question number 2, we have the same base again, x to the 5th times x to the 4th, the bases being x. So this is x to the 5 plus 4, which is x to the power of 9. The last one right here, now notice that we also just have the number 3 and the number 7 in front. So we know that when you multiply just numbers without powers, you can go ahead and multiply those together. So 3 times 7 is 21. You don't need to have those numbers be the same. We know that from elementary school. So again, variables though, when you multiply them, they do have to have the same base to add the exponent. Since the exponent's not there, it's just a 1, so that's 1 there. So that would be x to the 6 plus 1, and then y has the same base, so y to the, again, that's a 1 if it's not written, so 1 plus 9. And then, of course, we can simplify this. So 21 x to the power of 7, y to the power of 10. So again, make sure to multiply the coefficients. So multiply those coefficients, which again was the 7 and the 3. Now we have the quotient of powers. So for this, again, same thing, the bases must be the same. And of course, whatever is in our denominator cannot be equal to 0. So when we have the bases being that are the same and they're being divided, you subtract the exponent. So this is a to the power of m minus p. So subtract the exponents. So go ahead and pause the video, try 1, 2, 3 on your own. When you're done, on pause and check your work. So looking at number 1, notice that the bases are the same with the power. So we have 6 to the 5 minus 2, which is 6 to the power of 4. This is to the power of 3, which of course is numerical. So when we do this out, we get 216. And something that small you should be able to do in your head. So 6 times 6 is 36 times another 6 gives us 216. Looking at the next one, x to the 10th over x cubed. So same thing, same base, subtract the exponent. So x to the 10 minus 3, which is x to the power of 7. And here, now we see we have these numerical values in front, and then we have the same base and the same base here with the y's. So we have the 16 over 24, which we of course want to reduce, times x to the 7 minus power of 9, times y to the power of 8 minus 3. So 16 over 24 reduces into 2 over 3. Then we have x to the 7 minus 9, which is x to the negative 2 power, and 8 minus 3 is y to the 5th. Now, we're going to talk about this in just a minute as well for review, but remember, we're not supposed to have negative exponents. So when you have a negative exponent, only the term, which is this one right here, with the negative exponent moves. So if this is the only one with the negative exponent, that would go to the denominator. So this is actually equal to 2y to the 5th in the numerator, all divided by 3x, and then when you bring it down, that exponent becomes positive squared. And of course, that is the negative exponent rule, which we'll talk about in just a second if you forgot that one. The power of a power rule, remember again, same for this one, you don't have to have a same base. The power of powers when you have powers like this right here, which are on the outside of parentheses being multiplied. So for this one, you just multiply the exponents. So this one would be a to the power of m times p. So go ahead and pause, do these two, and then unpause when you're done. So here we have, again, power of power. So this would be 4 to the 3 times 2, which is 4 to the power of 6. And again, that's numerical, so 4,069. Sorry about the 96. Sorry, I wrote that backwards. So 4,096. And then for the next one, we have, again, power of power rule. Multiply those exponents. This is x to the 6 times the power of 8, which is 48. So x to the 48th power. Next one we have is power of a product. So power of a product means you have a power, and product means you're multiplying two bases. So power of a product, when it's inside parentheses, that means that each of these variables gets that power. So remember, this is really to the power of 1 and 1 here. So you really just multiplying those exponents like up here with the power of power. So this would be a to the 1 times m, which is m, and b to the 1 times m, which is m. So again, multiply each base exponents. So go ahead and pause the video, do 1, 2, and 3, and then unpause when you're done. So here we would get this 4 to the power of 2 and 5 to the power of 2. Technically, since this is all numerical, you could do what's inside the parentheses. 4 times 5 is 20, and 20 squared. That would give you the same answer. But this is a lot easier because we know 4 squared is equal to 16 times 25. And then if you multiply that, you get 400. Here, same thing. We're going to use our power of product rule. So this would be 3 to the 2 times 2, which is 4. Multiply that by 2 to the 2 times 4, which is 8. And then we can go ahead and simplify this. 3 to the power of 4 is 81, and 2 to the power of 8 is 256, which gives us 20,736. Looking at question number 3, now we have something that's in front, so a coefficient. So that coefficient also, the bases are the exponents of the base get multiplied. So I would make sure if you have a negative to put that in parentheses. So I'm going to do negative 3 to the power of 3, and then this would be x to the 3 times 2, which is 6, and y to the 6 times 3, which is 18. Then remember, if you have a negative to odd power, it stays negative. So negative 3 to the power of 3 would be negative 27. X to the 6, y to the power of 18. The negative exponent rule, which we did on the quotient of powers right up here. So let's go ahead and actually look at the rule. So if you have a negative exponent, remember we don't like to have those in our final answer. It's not simplified. So if it's in the numerator, we move it down to the denominator and make it positive. If it's in the denominator, it's moved up to the numerator and becomes positive. So really this would be over 1 like this, but you don't need to write that over 1. Just a to the power of m is okay. So go ahead and pause the video, do 1, 2, and 3, and then unpause when you're done. So 5 negative 2 is the same thing as 1 over 5 squared. And of course, numerical, you can simplify this 1 over 25 because that's 5 squared. Looking at the next one, 1 over x to the negative 11th power. We don't like that negative exponent, so that goes up to numerator, x to the 11th. Here, we first need to do our product of a power. We have the 1 here, and we did that up here in this problem, so we know negative 3 to the 3rd power is actually negative 27. Then we have x to the negative 7 times 3, which is negative 21, and y to the 6 times 3, which is 18. And so that x to the negative 21 is the only one that's going to move because it's the only one with a negative exponent. Even though we have a negative 27 here, that exponent of the negative 27 is 1. So you only move the terms with a negative exponent. So this would be negative 27 y to the power of 18 divided by x to the power of 21. So be careful with that because a lot of times I see students think that because the negative here is in front, that the number 27 also goes in the denominator, but it does not. Anything to the 0 power is 1, except for, of course, 0. So 5 to the 0 power is 1. If you have something in parentheses to the 0 power, it's 1. That means this one right here, that 12 is not in the parentheses, so that 12 stays 12. So 12 times 1, which is, or excuse me, negative 12 times 1, which is negative 12. Looking at the power of a product. So, or power of a quotient, sorry. Power of product was up there. So power of a quotient is the same idea as a power of product is what I was trying to say. So you multiply the exponents. So this would be a to the m times p over b to the n times p. And of course, b cannot be equal to 0 because we cannot divide by 0. So go ahead and pause the video and do 1 and 2, and then unpause when you're done. So over here, we would have x to the 5 times 3, which is 15, over y to the 11 times 3, which is 33, and that's as far as we can simplify. Looking at the next one, we have, again, the power on the outside, so each of the powers is going to get that exponent. So for this one, you could do a couple things. You could simplify the 5 and the 10 first if you want, because it's a numerical, and you could simplify what's inside and then do the power, or you can multiply the powers first. I like to simplify what's on the inside because it makes then simplifying the problem easier, so I'm going to go ahead and do that first. So 5 over 10 we know is equal to 1/2. And then we have x to the 5th over x. So when you subtract these exponents, you would get x to the 5 minus 1, which is 4. And then 2 minus 7, which gives us negative 5. Again, we don't like that negative exponent, so this would be 1 times x to the 4th in the numerator. You don't need to write that 1 over 2y to the power of 5. And of course, that's all to the 4th power. And now I'm going to go ahead and do that power. So 4 times 4 gives me 16, so x to the 16 in my numerator. And remember that 2 has a power of 1, so 1 times 4 is 2, so 2 to the power of 4. And y to the 5 times 4 is 20. And of course, the 2 to the 4th is numerical, so we can go ahead and computate that. That's equal to 16. So x to the 16 over 16, y to the power of 20. And of course, that is not the only way we could have solved this, but that is just one way. You could have done the power of the powers first by multiplying. So here is a note. It says the properties of exponents work only for multiplication and division. So be very careful. When you introduce addition or subtraction, this does not work. And so if I have a plus b to the power of n, it does not equal a to the n plus b to the n. Same thing with a minus b to the n. It does not equal a to the n minus b to the n. Remember that this is a binomial to a power, so you have to FOIL that out. So like if I had, for instance, a plus b squared, remember that means you have two of these binomial terms, a plus b times a plus b, and then you have to FOIL. So first, outside, inside, last. So this would be a times a is a squared plus ab plus ab again, and then plus b squared. So this is a squared plus, and these are like terms because they have the same variables to the same power, so 2ab plus b squared. So again, notice that if you were to use those rules when you have addition or subtraction between, then you're missing that middle term. So again, these powers or properties only work for multiplication and division. When you're simplifying exponential expressions, just keep this in mind. Simplified means that there's no parentheses in your final answer, no powers raised to powers, no negative exponents, and always simplify numerical expressions. So that's just kind of an review of what we just talked about. So let's go ahead to the next part. Just as a reminder, adding and subtracting monomial terms. Remember, monomial just means one term, binomials two terms, trinomials three. But again, remember when there's a binomial to a power or something, we can't use these rules. So when you're adding and subtracting terms, remember that you want to combine like terms. Like terms are same variables to the same power. And remember, you do not change the common variables and exponents. So you keep those the same. So if I look here, notice that this has the same variables to the same power, so these are like terms. So what do? You change the coefficients doing the operation, which in this case is subtraction. So 9 minus 10 is negative 1, so this is negative 1 x squared y, or you could just write negative x squared y. It's the same thing. You don't need that one placeholder. So here, what are our like terms? These two are like terms with the x's. So we have to subtract the coefficients in this case. So 3 minus 5, which is negative 2, so negative 2x. And then notice that these have the variables to the same power, so those are like terms. So now we're adding the coefficients. 4 plus 3 is 7, so plus 7x squared z. So just don't get confused with that and with what we just did with the exponent rules. Looking at the next part, so far we've worked with integer exponents only. This is not the only type of number we can have for an exponent. Many times we will have rational numbers or fractions as exponents. Rational exponents are another way of writing radicals. So remember we learned that last year. So another way of writing a radical. So for this, rational exponents, if I have a to the power of n over d, recall that we can rewrite this as a radical. This is the number on the bottom becomes the index of the root, so this is the d root of a to the power of n. Or you could also write this as the d root of a all to the power of n. We usually don't write it the second way, usually I write it the first way. So over here with numbers, if I have x to the 2/3 power, that is the cube root of x squared, or you could write this as the cube root of x all squared, but again, usually I write it like this. Recall that the index is always in the denominator of the rational exponent. So again, the index is what you're taking your root of, so the index here was 3. So let's go ahead and put this into some practice. So go ahead and take a moment to do 1 through 7 on your own and then on pause when you're done. So looking at the first one, we're just going to rewrite this, each exponential expression in radical form. So we're not going to simplify. So I'm going to make a note. We can simplify these, but for our purposes, we're just going to rewrite it in the form just so we can practice it. So this would be the 5th root of 2 squared. And this would be equal to the square root. And usually if you have an index of 2, you don't write it. So of 3 to the power of 3. And again, these do simplify because really we know 2 squared is 4. So we're just going to leave our answers like this right now. So really we know this is equal to the 5th root of 4. And really we know this is equal to the square root of 27. But again, we're just going to leave our answer with the form we just did, so without simplifying it. So this would be the 8th root of 7 to the power of 5. And again, we know we can simplify 7 to the 5th. It's numerical. So I guess we might as well just go ahead and and simplify them since you might have already done that. So this would be the 8th root of 16,807. This is equal to the 5th root of 5 to the power of 6. Um, that means we have one group of 6, and this is an index of 5, which means we're looking for groups of 5. Just like if we have a cube root index, you would look for groups of 3. If this was a 4th root index, you look for groups of 4 to take out. So that means we have 5 times 5 times 5 times 5, 6 times. And so this makes a group of 5. So that means you can take a 5 out, and then 1 5 is left underneath. So this would be the 5th root. The 5 goes on the outside, so 5 times the 5th root of 5 would actually be simplified. For this one, notice that this is in parentheses all to the 1/3 power. So this is the cube root of 3 to the power of 1, and x to the 7 times 1, which would just be x to the 7th. And this is not simplified because this is an index of 3, which means we're looking for groups of 3. This is x times x 7 times. So we have two groups of 3 with 1 left over. So this is actually equal to the cube root, and the x squared would go on the outside because we have two groups that grow out, so x squared. And this would be 3 to the x. So this would be simplified. Looking at this next one, we have the 6th root of 24 to the 5th power, x to the 5 times 4 is 20. And again, we can simplify this, but I'm just going to leave my answer like this for right now. And for this one over here, that 8 is not to the 3/5 power, so that stays on the outside of the radical. And this would be the 5th root of 5 to the 3rd, x to the 2 times 3, which is 6. And again, we can simplify this, but I'm going to go ahead and leave my answer like this for right now. All right, looking at the next one, let's try using our exponent rule, simplify each expression. So for these, go ahead and do this on your own, and then when you're done, you can unpause it. So here, for number 8, we have the same base being multiplied, so you add the exponent. So this would be 10 to the 1/2 plus 3/2. We have the same denominator, so you need a common denominator to add fractions or subtract them. So that means this is 10 to the 4/2, which is 10 squared, which is 100. Over here, we have x, and you have a power rule, so you multiply it. 2/3 times -3 is just -2. We don't like to have negative exponents, so that becomes 1 over x squared. Over here, power rule, multiply the exponents. So 3 to the 1 times -4 is -4. X to the, and this becomes negative 8/3. And then we don't like to have negative exponents, so 1 over 3 to the 4th, x to the 8/3, which becomes 3 to the 4th is numeric, so 81, x to the 8/3. Now 8/3 we can write in radical form, but it's not asking us to do that. It just says to simplify using our properties of exponents, so we're just going to leave it like this for right now. We have right here 3 to the 1/2 times 12 to the 1/2. These are not the same bases, so we can't just add the exponents. But let's go ahead and rewrite this to see if that helps us simplify. This is the 1/2, so the index is 2, so the square root of 3 to the 1st power times the square root of 12. Well, we know rules of radicals. If you have two radicals that are being multiplied, you can multiply what's underneath. So really this is the square root of 3 times 12, which is 36. And then we know the square root of 36 is equal to 6. Another way you could think about that is by splitting this up. 3 times 4 is 12 to the 1/2 power. So this would be 3 to the 1/2 times 3 to the 1/2 times 4 to the 1/2 power. And so something with the same base, add the exponents, 1/2 and 1/2. That gives you 1. So this is 3 times 4 to the 1/2 is the square root of 4, which is just 2, and 3 times 2 is 6. So that's another way of thinking about the problem. For question number 12, power rule. So x to the -6 times 1/2 would give us -3. This would be y to the power of 4. We don't like the negative exponent, so y to the 4 over x to the power of 3. For question 13, we want to again multiply the exponents. So x to the 12 over 4, which is 3, and then y to the -3/4 times 12 gives us -9. Again, negative exponent, we need to bring that up to the numerator because it's in the denominator, so x to the third, y to the power of 9. Here we have the same base being divided, so we're going to subtract those exponents. So this is x to the 5/6 minus 1/3. In order to do this problem, we need a common denominator. So multiply this by 2 over 2, so you have your common denominator 6. So 5 over 6 minus 2 over 6, which is equal to, subtract the numerator, 3 over 6, which is 1/2. So really this is x to the power of 1/2. And of course that is also equal to the square root of x, but it said to simplify using our exponent rule, so we're going to leave it with x to the 1/2. Looking at the next one, we have power rule, so you can simplify inside first if you can, or reduce through the power. It's just personal preference. So 16 to the 1/2, x to the 14 times 1/2 is 14 over 2, or 7, 81 to the 1/2, and y to the 18 times 1/2, or divided by 2, is 9. 16 to the 1/2 is really the square root of 16, and this is the square root of 81. Square root of 16 we know is 4. Square root of 81 we know is 9. And that's it. So let's look at solving exponential equations. So we're going to solve by equating the exponents. So if b to the power y equals b to the power x, that's only true if and only if the exponents x equals y. Sometimes you will need to rewrite the bases so that they are the same if they are not. Here we have the same bases, they're equal, therefore x has to be equal to 3. Over here, same base, therefore 2x plus 3 has to be equal to 4x minus 5, and then you're just solving the equation. So get your like terms together, subtract the 2 to the other side to get the x's together. And then we want to get the 5 to the other side to get the numerical terms 3 and 5 together. Solve for x, divide by 2. So x is equal to 4, and of course you could always plug that into both sides to make sure they are equal to check. Here, notice that the bases are not the same. So when that happens, you always want to look at the smaller number. You don't want to go up in terms because that changed your equation, but going down does not. So 4 is a smaller number out of the two. So can I make 16 into a base of 4? I can, because we know that's 4 squared. So this stays 4, 3x plus 5 equals, this is really 4 squared to the 2x plus 1. So again, always use the smaller number. You wouldn't want to do this as 4 squared because then that changes the problem. So now we have the same base, we can set the exponents equal. So we have 3x plus 5 equals 2 times 2x plus 1. Notice I put it in parentheses because both of these terms have to be multiplied. So 3x plus 5 equals 4x plus 2 when you distribute, and then combine your like terms minus the 3x. 5 is equal to x plus 2, subtract the 2. 3 is equal to x, and then of course you could plug it into your equation for x to make sure both sides are equal to check your work. Over here, same thing, we have 81 and 1/3, which do not look like the same bases to me, so we're going to look at the smaller one to help us. I don't usually like working with fractions, so I'm going to make this a negative power, so we would get 81 3 minus x. How do I make this a negative power? By taking this up and getting rid of that fraction. So this would be 3 to the negative 1 power is the same thing as 1/3. I just like to do that because then that helps me see, okay, well then can I make 81 into a power of 3? Yes, I can. It's a lot easier to see that than think about 1/3. So I know that 3 to the power 4 is 81. So 3 to the power 4 all to the 3 minus x equals, this is 3 to the negative 1, and then 5x minus 6. So now that the bases are the same, we can set the exponents equal. So 4 times 3 minus x is equal to negative 1 times 5x minus 6. Distribute those values. So 12, um, 12 minus 4x equals negative 5x plus 6. And then I'm going to add the 5x. So 12 plus x equals 6. Subtract the 12, and x is equal to negative 6. And then, of course, you could plug it in to check your work. The next problem is going to be looking at logarithmic and exponential expressions, which is something that we are going to be focusing on for this unit. This is just getting into what the whole unit is going to be about, which is the fact that these two functions are inverses of each other, which we're going to be talking more about in the next section. So for this reads right here, the log base b of y equals x. So that's how you read it. So the log base b of y equals x if and only if b to the power of x equals y. I'm going to write this out. So the log, the b is the base of, I'm going to call this a equals e. And so in exponential form, this would be the base of e equals a. So these two are inverses of each other. So logarithm is an inverse of something that's exponential. And again, we're going to talk a little bit more about this soon. But for this, b and y are always positive, and b cannot be equal to 1. And we'll talk more about that in a little later. So for this, if we want to rewrite this logarithmic expression in exponential form, you're going to use that rule that we have. So the base always stays the base. The answer to a log is the exponent. And the answer switches to the other side. So the way that I like to look at it is I do what's called the loop rule. So this loops around to what you're taking the log of. So 2 to the power of 5 equals 32. And of course you could check, does 2 to the power of 5 equal 32? Yes, it does. So we have the 7. This loops back around to what you're taking the log of. So this reads log base 7 of 1 equals 0. This one read log base 2 of 32 equals 5. So 7 to the power of 0 equals 1, which it does. And here, same thing, we have the 13, loop it around to what you're taking the log of. So 13 to the power of 1 equals 13, which is, of course, true. Now we're going to rewrite the exponential equations in logarithmic form. So the base always stays the base. So what's the base here? 1/2. So this is the log. The base is 1/2, so it's 1/2 here. And notice it's a subscript, so always try to write that smaller, of what number equals what. So the answer to a log is an exponent. That is why we like logarithms, because it helps us to solve for exponents. So log base 1/2 of 2 equals the exponent -1 would be how we write that. 5 to the power 3 equals 125. So as a logarithm, 5, the base stays the base. So 5 to the base of 5, or excuse me, log base 5 of 125 equals the exponent 3. The answer to a log is always an exponent. Over here, try to do this one on your own. So for this one, log base 8 of 2 equals the exponent x. And again, we're going to talk more about logarithmic form in the next section. I just kind of wanted to have you guys take a look at it to get a little ahead of ourselves. And that'll be all for today.